Everything you thought you knew about our cosmic neighborhood is wrong. Dead wrong. For centuries, we've been taught to imagine the solar system as a tidy collection of planets orbiting peacefully around our sun, a cosmic carousel spinning in the darkness, isolated and alone in the vast ocean of space. We've drawn it in textbooks with neat circles, labeled it with confident precision, marked its boundaries with the orbit of Neptune, or perhaps Pluto if we're feeling generous. But here's the truth that will shake you to your core. The solar system doesn't end where we thought it did, not even close. The revelation came slowly, like dawn breaking over a landscape we thought we knew. It started with whispers from the edges, anomalies that didn't fit our neat models, objects that shouldn't exist where they were found, movements that defied our expectations. And then, piece by piece, observation by painstaking observation, a new picture emerged. A picture so vast, so incomprehensibly enormous, that it makes our previous understanding look like a child's drawing compared to a masterpiece. Imagine standing on a beach, watching waves crash against the shore. You think you understand the ocean because you can see the waves, feel the spray, hear the roar of breaking water. But beneath those waves lies an entire world. Depths beyond depths, mountains and valleys and creatures that have never seen light. The visible surface is merely a hint, a whisper, a suggestion of what truly exists below. This is our solar system. What we see, what we've always seen, is just the surface. The true extent of our cosmic home stretches so far into the darkness that it touches the realm of other stars, interweaving with them in a cosmic dance we're only beginning to understand. The old theory was comfortable. It was safe. Picture it like this. Imagine the sun as a bonfire on a dark prairie night. The planets are dancers circling that fire, each in their own ring, moving to an ancient rhythm. Mercury dances closest, feeling the full heat of the flames. Venus next, then Earth, then Mars. The outer dancers, the giants Jupiter and Saturn, Uranus and Neptune, circle at a more stately pace, their movements slow and majestic. And beyond them, we thought there was nothing, just darkness, just void, just the empty space between stars, cold and dead and utterly vacant. But we were so wrong, it's almost embarrassing. It's as if we declared that a city ends at its downtown core, ignoring the suburbs, the farmlands, the distant mountains on the horizon that still belong to this same geographic region. The reality is that our solar system is not a small island of light in an ocean of darkness. It's a vast empire, a sprawling domain that extends so far that measuring it makes our heads spin and our minds rebel against the numbers. Let's start with what we can barely comprehend. The Oort cloud. Say that name slowly. The Oort cloud. It sounds almost mystical, doesn't it? Named after the Dutch astronomer Jan Oort, who proposed its existence back in 1950, this isn't just some minor feature at the edge of our cosmic neighborhood. No, this is a shell, a sphere, a vast encompassing cocoon of icy bodies that surrounds everything we've ever thought of as the solar system. Everything. Think about that for a moment. Every planet, every asteroid, every comet you've ever heard of, every space probe we've ever launched, all of human civilization, Earth itself, the sun that gives us life, Jupiter with its massive gravitational pull, Saturn with its glorious rings, Neptune at what we once thought was the frontier of our realm, all of it, sits inside this cloud like a pearl inside an oyster shell. Except this shell is so large that it beggars belief. How large? Are you ready for this? The Oort cloud might extend from about 2,000 astronomical units from the sun out to maybe 100,000 astronomical units. Maybe more, maybe much more. An astronomical unit, remember, is the distance from Earth to the sun, about 93 million miles, about 150 million kilometers. It's the distance light travels in about 8 minutes. Now multiply that by 100,000. 100,000 times the distance from Earth to the sun. Let me put this another way that might help your brain grasp the sheer insanity of these distances. Neptune, the most distant planet in our solar system, orbits at about 30 astronomical units from the sun. 30. The Oort cloud extends to perhaps 100,000 astronomical units. That means the true edge of the solar system is more than 3,000 times farther than Neptune. 3,000 times. If you were to build a scale model of the solar system where Earth was the size of a peppercorn, and you placed it 1 meter from the sun the size of a large beach ball, do you know where you'd have to place the outer edge of the Oort cloud? Approximately 15 kilometers away, nearly 10 miles. That's not a model you can build in a classroom. That's not a model you can build in a stadium. You'd need a small city to contain it. But here's where it gets even more mind-bending, even more reality-shattering. At those distances, at the outer reaches of the Oort cloud, our sun's gravity is so weak, so tenuous, so barely present, that these icy objects are almost as influenced by the gravity of other stars as they are by our own sun. They exist in a twilight zone, a boundary region where our solar system blurs into interstellar space, where the definition of ours versus not ours becomes fuzzy and uncertain. These objects in the Oort cloud, trillions of them, perhaps hundreds of trillions, are the leftover building blocks of the solar system, the raw material that didn't get incorporated into planets or moons or asteroids. They've been out there for 4.5 billion years, slowly orbiting in the darkness, so far from the sun that its light is barely distinguishable from other stars. Out there, the sun is just another bright point in the sky, barely brighter than others. Certainly not the life-giving furnace we know on Earth. And these aren't small objects. We're talking about chunks of ice and rock, some as small as mountains, some as large as cities, some perhaps as large as dwarf planets. They orbit in a vast shell in all directions, above and below the plane where the planets orbit, surrounding us completely, three-dimensionally. The solar system isn't a flat disk as we often imagine it. It's a sphere, a bubble, a three-dimensional domain with us at the center. Now here's the shocking part, the part that changes everything. We think the Oort cloud occasionally sends visitors to the inner solar system. These are the long-period comets, the ones that take thousands or millions of years to complete a single orbit. When something disturbs an Oort cloud object, perhaps the gravitational nudge of a passing star, perhaps the subtle pull of the galactic tide, perhaps the influence of a massive planet we haven't discovered yet lurking in the darkness, that object can fall inward, beginning a million-year journey towards the sun. As it falls inward, as it gets closer to the warmth of the sun, the ice begins to vaporize, creating the spectacular tails we associate with comets. These are messengers from the edge of the solar system, travelers from the abyss, bringing us information about conditions in that distant realm. Every comet we see is a postcard from the frontier, a glimpse of what exists in that vast shell surrounding us. But wait, there's more. There's always more. Because between Neptune and the Oort cloud lies another realm, another collection of objects that we're only beginning to understand. This is the scattered disk, the detached objects, the region where gravity from Neptune has flung objects into strange, elongated orbits that take them far beyond the main planets, but not quite as far as the Oort cloud. This region is bizarre. It's populated by objects with orbits so elliptical, so stretched out, that they spend most of their time in the darkness and cold beyond Neptune, only occasionally swooping closer to the sun. Some of these orbits are tilted at crazy angles to the plane where the planets orbit. Some of them are so strange that scientists scratch their heads trying to explain how they got that way. Take Sedna, for example. Beautiful, mysterious Sedna. This is a dwarf planet, about 3/4 the size of Pluto, that never gets closer to the sun than 76 astronomical units. Never. Even at its closest approach, it's more than twice as far as Neptune. And at its farthest point, it reaches out to 937 astronomical units. 937 times the distance from Earth to the sun. Its orbit takes 11,400 years to complete. 11,000 years! Entire civilizations rise and fall in less time than it takes Sedna to go once around the sun. How did Sedna get into such a strange orbit? Nobody knows for certain. The mathematics don't quite work out with our current understanding. Neptune's gravity can't explain it. There's something else out there, something massive, something that perturbed Sedna's orbit in the distant past and sent it into this bizarre trajectory. What could that be? A rogue planet? A passing star billions of years ago? Something else entirely? And Sedna is not alone. We've found other objects with similarly strange orbits, objects that seem to be pointing us toward a profound mystery lurking in the darkness beyond Neptune. Objects like 2012 VP113, like 2015 TG387, objects with orbits that align in ways that seem too coincidental to be random. Their orbits point in similar directions, tilted at similar angles, as if they're all responding to the same massive gravitational influence. This has led to one of the most exciting and controversial ideas in modern astronomy: Planet 9, or Planet X, or whatever you want to call it. The idea is simple but staggering. There might be another planet in our solar system, a real planet, massive and distant, that we haven't discovered yet. Not a dwarf planet like Pluto, a real planet. Perhaps 5 to 10 times the mass of Earth, perhaps orbiting at 400 to 800 astronomical units from the Sun, perhaps taking 10,000 to 20,000 years to complete a single orbit. Can you imagine that? Another planet in our solar system, in the 21st century. How is that possible? But the mathematics are compelling. The orbital patterns of these distant objects make sense if there's a massive planet out there, shepherding them, perturbing their paths, keeping them clustered in certain configurations. The computer simulations show it, the statistical analyses suggest it, the orbital mechanics demand it. And yet we haven't seen it. We haven't found it. It's out there somewhere in the darkness, in a realm so vast and so poorly surveyed that a planet 5 times the mass of Earth could hide from us. Think about that for a moment. We've sent probes to Pluto. We've photographed galaxies billions of light years away. We've detected planets orbiting other stars hundreds of light years distant. And yet, right here, in our own cosmic backyard, there might be a planet we've never seen. The universe is not done surprising us. The solar system is not done revealing its secrets. But let's go back. Let's talk about what lies above and below, because that's what truly shatters our understanding of cosmic geography. When we look at diagrams of the solar system, we almost always see it from the side or from above, showing the planets in a neat line or in neat circles around the Sun. This gives us the impression that the solar system is flat, that everything orbits in the same plane, that above and below the planets there's nothing but empty space stretching to the stars. This is a lie of convenience, a simplification that has blinded us to the true nature of our cosmic home. The planets do mostly orbit in the same plane, that's true. This plane is called the ecliptic, and it's defined by Earth's orbit around the Sun. The other planets orbit close to this plane, within a few degrees of it, because they all formed from the same rotating disk of gas and dust billions of years ago. But beyond the planets, in the Kuiper belt, in the scattered disk, in the Oort cloud, objects orbit in all directions, above the ecliptic, below the ecliptic, at every possible angle. The Oort cloud, remember, is a sphere. It surrounds us completely. That means there's just as many icy bodies above the plane of the solar system as there are below it, just as many to the north as to the south. The Sun sits at the center of this vast sphere, and from any object in the Oort cloud, the Sun is just a bright star, and the planets are invisible, and the concept of above or below becomes meaningless. But there's something else up there, above and below the solar system, something even more profound, something that connects us to the galaxy itself. The solar system, you see, is not stationary. It's not floating peacefully in some fixed location in space. No, it's moving,
moving fast. Our entire solar system, sun and planets and Oort cloud and all, is orbiting the center of the Milky Way galaxy at about 230 kilometers per second. That's more than 500,000 miles per hour. We're screaming through space, completing one orbit around the galactic center every 225 to 250 million years. The last time we were at this point in our orbit, dinosaurs had just begun to walk the Earth. As we orbit, we're not moving in a perfect circle. We're moving in a spiral, bobbing up and down relative to the galactic plane, like a horse on a cosmic carousel. Right now, we're slightly above the galactic plane, moving upward. In about 30 million years, we'll reach the peak of our upward journey, about 230 light years above the galactic plane. Then we'll start falling back down, crossing through the galactic plane, continuing down to about 230 light years below it, then rising again, up and down, a cosmic oscillation that takes 64 million years to complete.
Why does this matter? Because the galactic plane is where most of the galaxy's matter is concentrated. The disk of the Milky Way, seen from the side, looks like a flattened sphere with a bulge in the middle. Most of the stars, most of the gas, most of the dust, most of the mass is concentrated in this disk. When we pass through the galactic plane, we're passing through denser regions of space, more matter, more gravitational influences, more potential disturbances. Some scientists have suggested that these passages through the galactic plane might trigger events in the solar system. They might disturb the Oort cloud, sending showers of comets toward the inner solar system. They might increase the rate of impacts on Earth. They might even correlate with mass extinction events in Earth's history. The evidence is controversial, debated, uncertain. But the idea is haunting, that events in Earth's history, events that shaped the evolution of life, might be connected to our position above or below the galactic plane. So when we ask what lies above and below the solar system, part of the answer is the galaxy itself. The vast structure of the Milky Way, with its spiral arms, its central bulge, its halo of ancient stars, its dark matter corona. We are embedded in this structure. We are part of it. The solar system is not separate from the galaxy. It's a tiny component of something vastly larger. And there's more still, because even the galaxy is not the end of the story. Above and below the Milky Way, extending far beyond its visible disk, is what astronomers call the galactic halo. This is a roughly spherical region, much larger than the galaxy's disk, populated by old stars, globular clusters, and, most intriguingly, by vast amounts of dark matter. Dark matter. Those two words alone should make you shiver with excitement and frustration. We know dark matter exists. We can measure its gravitational effects. We can see how it bends light from distant galaxies, how it holds galaxy clusters together, how it shapes the structure of the universe itself. But we don't know what it is. We've never detected a particle of dark matter directly. It doesn't emit light. It doesn't absorb light. It doesn't interact with normal matter except through gravity. It's invisible, intangible, ghost-like, and it's everywhere. The galactic halo is dominated by dark matter. There's far more dark matter in the Milky Way than there is normal matter. The stars, the gas, the planets, the people, everything we can see and touch, all of it makes up only about 15% of the galaxy's total mass. The rest is dark matter, surrounding us, passing through us, holding the galaxy together with its gravity, and yet completely invisible to our eyes and our telescopes. So above and below the solar system, there's this vast halo of dark matter, extending perhaps 300,000 light-years from the galactic center, dwarfing the visible galaxy.
We're swimming in it. Earth is moving through dark matter right now. Dark matter particles are passing through your body right now, billions of them every second, and you don't feel a thing because they don't interact with normal matter. Isn't that extraordinary? Isn't that humbling? We think we know what the universe is made of, but 85% of its matter is something we can't see, can't touch, can't directly detect. We only know it's there because of its gravitational effects. It's as if we're fish in an ocean, able to see other fish in the water around us, but completely unable to perceive the pressure of the water, unable to understand that we're surrounded by this medium that shapes everything about our environment. But let's come back to something we can observe, something more tangible. Let's talk about the heliosphere, because this is one of the most beautiful and least appreciated structures in the solar system. The heliosphere is a bubble, a vast protective bubble that the sun creates around itself and everything inside the solar system. Here's how it works. The sun doesn't just emit light, it emits a constant stream of charged particles, protons and electrons, streaming outward in all directions at speeds of 300 to 800 kilometers per second. This is the solar wind, and it's blowing all the time, day and night, year after year, century after century, for as long as the sun has been shining. This solar wind is thin, incredibly thin. In near-Earth space, there are only about 5 to 10 particles per cubic centimeter. That's far less than the best vacuum we can create in a laboratory. But it's there, and it's moving fast, and it carries the sun's magnetic field with it, stretching it out into space like a garden hose being dragged across a lawn. This solar wind keeps blowing outward until it hits something. What does it hit? The interstellar medium, the gas and particles that exist between the stars. This interstellar medium is even thinner than the solar wind, only about 0.1 particles per cubic centimeter. But it exists, filling the galaxy, and it has its own magnetic field, its own pressure, its own properties. Where the solar wind meets the interstellar medium, a boundary forms. The solar wind slows down, compresses, piles up against the resistance of the interstellar medium. This boundary, this collision zone, creates the heliosphere. The heliosphere is the region of space where the solar wind dominates, where the sun's magnetic field is stronger than the interstellar magnetic field, where the environment is shaped by our star rather than by the galaxy at large. And the heliosphere is huge. Its exact size and shape depend on how fast the solar wind is blowing and how dense the interstellar medium is in our current location. But estimates suggest that the heliosphere extends perhaps 100 to 120 astronomical units from the sun in the direction of our motion through the galaxy, and perhaps 200 to 300 astronomical units or more in the opposite direction, creating a teardrop or comet-like shape with a long tail streaming behind us. Think about that. The heliosphere extends well beyond the orbit of Pluto, well beyond the Kuiper belt, encompassing all the planets and most of the known dwarf planets. It's like a force field, a protective shield that the sun creates around us. And it protects us in a very real way. Because outside the heliosphere, in the interstellar medium, there are cosmic rays. Cosmic rays are high-energy particles, mostly protons, accelerated to near light speed by supernova explosions, by pulsars, by black holes, by violent events in the galaxy. These particles carry enormous energy, and when they hit molecules in Earth's atmosphere, they create cascades of secondary particles. Some cosmic rays make it all the way to Earth's surface. They pass through us. They can damage DNA. They're one of the reasons life on Earth had to develop mechanisms to repair genetic damage. But the heliosphere blocks most of them. The solar wind, thin as it is, and the magnetic field embedded in it, deflects and slows cosmic rays. The heliosphere is like an umbrella in a rain of high-energy particles. It's not perfect protection. Plenty of cosmic rays still get through, but without it, the radiation environment in the inner solar system would be much more dangerous. Life on Earth might have evolved differently, or might have been much more difficult to sustain. We know this because we've sent probes outside the heliosphere. Voyager 1 and Voyager 2, those ancient spacecraft launched in 1977, are now in interstellar space, beyond the protective bubble of the heliosphere. Voyager 1 crossed the boundary in August 2012 at a distance of about 122 astronomical units from the Sun. Voyager 2 crossed in November 2018 at about 119 astronomical units. They're out there right now, still sending back data, still functioning after more than 4 decades, reporting on conditions in the space between stars. And what they found is fascinating. The interstellar medium is denser than we expected. The magnetic field is stronger. The cosmic ray environment is more intense. The boundary of the heliosphere, called the heliopause, is not a sharp edge, but a complex region with multiple layers and structures. The heliosphere itself seems to be changing shape, buffeted by variations in the interstellar medium as we move through it. So above and below the solar system, surrounding it on all sides, is this bubble, this heliosphere, created by the sun's breath, protecting the planets from the harsh environment of interstellar space. And beyond it is the true frontier, the realm between stars, where no human presence has ever existed except for 2 small probes, now more than 15 billion miles away, still calling home with their faint signals. But even the heliosphere is not the largest structure associated with the Sun, because the Sun, like all stars, is not alone in its journey through the galaxy. Stars don't form in isolation. They form in clusters, in groups, in associations of hundreds or thousands of stars, all born from the same giant molecular cloud. Over time, these clusters spread out, their members drifting apart, scattered by the galaxy's gravitational tides. But they don't forget each other. They remain loosely associated, moving through the galaxy in similar directions at similar speeds for hundreds of millions of years. The Sun was born in such a cluster 4.6 billion years ago. Its siblings have long since scattered across the galaxy, but they're out there somewhere, stars that formed from the same cloud of gas and dust that made our Sun. Some of them might be very much like the Sun. Some of them might have planets. Some of those planets might have life. We might have cousins out there, life forms that evolved on planets orbiting the Sun's stellar siblings, and we would never know it. Scientists have tried to identify these sibling stars by analyzing stellar motions and compositions, looking for stars whose trajectories, when wound backward through time, converge on the same point where the Sun was 4.6 billion years ago. They found a few candidates, stars scattered across the sky, some of them hundreds of light years away. These stars share a common heritage with our Sun. They're family in a cosmic sense. And here's a thought that should make you pause. In the cluster where the Sun was born, the stars were much closer together than they are now, perhaps only 1 or 2 light years apart, maybe even closer. At those distances, the Oort clouds of neighboring stars might have overlapped. Objects might have been exchanged between stellar systems. A comet that formed in another star's system might have been captured by the Sun's gravity. That means some of the comets in our Oort cloud might not be native to the solar system at all. They might be immigrants, refugees from other stellar systems, carrying with them the chemical signatures of their birthplaces. And if comets can move between systems, what else can? Could life have spread between stars in the Sun's birth cluster? Could microbes, hardy bacteria encased in rocks blasted off the surface of a planet by an asteroid impact, survive the cold of space for millions of years and land on a planet in another system? This idea, called panspermia, is controversial but not impossible. Life on Earth might have originated on another planet orbiting one of the Sun's siblings, or life from Earth might have seeded planets around other stars. We are all potentially related, not just to life on Earth, but to life across multiple star systems. These are the kinds of thoughts that emerge when we truly contemplate what lies above and below the solar system. Because it's not just empty space. It's not just darkness. It's a rich, complex, interconnected environment. The solar system is embedded in the galaxy. The galaxy is embedded in the local group of galaxies. The local group is embedded in the Virgo supercluster. The Virgo supercluster is embedded in an even larger structure called Laniakea. Everything is connected. Everything influences everything else. And let's not forget about the cosmic web, that vast network of filaments and voids that defines the largest structure in the universe. Galaxies are not randomly distributed through space. They're arranged in filaments, long chains and walls of galaxies separated by enormous voids where few galaxies exist. The Milky Way is part of one of these filaments. Above and below the filament, there are voids, regions millions of light years across that contain very few galaxies. These voids are not empty. They contain dark matter. They contain some gas. They contain some isolated galaxies. But they're underdense regions, areas where the universe has expanded more than average, where matter has been pulled away toward the denser filaments by gravity. The voids are like the gaps in a sponge, and the filaments are like the material of the sponge itself.
The solar system, the sun, our Earth, we all exist in a filament of this cosmic web. Above and below us, on the largest scales imaginable, are these vast, empty regions stretching across hundreds of millions of light years. And beyond that, more filaments, more voids. The pattern repeating on scales so vast that light takes billions of years to cross them. But let's bring it back to something more immediate, more visceral. Let's talk about what's directly above Earth, in the space immediately surrounding our planet, because even this region is far stranger and more complex than most people realize. Above the atmosphere, above the thin blue line that marks the boundary between air and space, there's a region called the magnetosphere. This is Earth's magnetic field, extending far into space, shaped by the solar wind into a teardrop shape, similar to the heliosphere, but much smaller. The magnetosphere protects us from the solar wind, deflecting the charged particles before they can reach the atmosphere, channeling them toward the poles where they create the aurora borealis and aurora australis. The magnetosphere is not empty. It's filled with trapped particles, electrons and protons caught in Earth's magnetic field, spiraling back and forth between the poles. These trapped particles form regions called the Van Allen radiation belts, named after the physicist James Van Allen, who discovered them in 1958. There are two main belts, an inner one and an outer one, sitting like donuts around Earth, above the equator. These radiation belts are dangerous. The particles in them carry enough energy to damage spacecraft electronics and harm astronauts. Satellites passing through the belts can experience glitches and failures. The International Space Station orbits below the inner belt, but astronauts traveling to the moon must pass through both belts, receiving a dose of radiation in the process. Future missions to Mars will have to deal with this hazard, finding ways to shield crew members during the passage through the belts. But the Van Allen belts are dynamic, changing in response to solar activity. During solar storms, when the sun ejects massive bursts of charged particles toward Earth, the belts can swell, becoming larger and more intense. Sometimes a third belt appears temporarily. The outer belt can be depleted or enhanced depending on conditions. The magnetosphere is constantly in flux, responding to the ever-changing solar wind. And beyond the magnetosphere, at a distance of about 90 Earth radii, there's a region where Earth's magnetic field lines reconnect with the interplanetary magnetic field carried by the solar wind. This region, called the magnetopause, is where Earth's domain ends and the solar wind's domain begins.
It's a boundary, a frontier, a place where opposing magnetic fields clash and merge, releasing energy in the process. So even in near-Earth space, there's complexity, structure, danger, and beauty. The space above Earth is not empty. It's filled with fields, particles, and phenomena. It's an environment just as real and just as complex as the ocean or the atmosphere. But let's zoom out again. Let's think about the long-term future, because the structures above and below the solar system will change over time. The Oort cloud is not stable forever. Stars pass by, perturbing the orbits of Oort cloud objects, potentially stripping some of them away. In about 1 billion years, if our galaxy merges with the Andromeda galaxy as predicted, the gravitational chaos of the merger might disrupt the Oort cloud dramatically, sending a storm of comets into the inner solar system or ejecting them into intergalactic space. The Sun itself is changing. It's slowly getting brighter as it ages, burning hydrogen into helium in its core. In about 1 billion years, Earth will become too hot for life as we know it. The oceans will evaporate, the atmosphere will be stripped away. Earth will become a barren, scorched rock. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. It will expand into a red giant, swallowing Mercury and Venus, possibly reaching all the way to Earth's orbit. When the Sun becomes a red giant, the outer solar system will warm up. The moons of Jupiter and Saturn might become habitable, at least temporarily. Europa's ice might melt, revealing the ocean beneath. Titan's methane lakes might evaporate. The Kuiper Belt and the Oort cloud will be affected by the increased solar wind from the dying Sun. Their ices sublining, creating a spectacular display of comets as trillions of objects begin to outgas. Eventually, the Sun will shed its outer layers, creating a planetary nebula, a beautiful expanding shell of gas illuminated by the hot core of the Sun, now a white dwarf. The white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder, no longer emitting any light. The planets, if any survive, will orbit in eternal darkness, frozen and dead. But that's billions of years in the future. For now, the solar system is vibrant, dynamic, full of mysteries waiting to be uncovered. And the mysteries above and below our cosmic neighborhood are some of the most tantalizing of all. Consider the galactic halo again, that vast region surrounding the Milky Way, populated by old stars and dominated by dark matter. Some of these stars in the halo are among the oldest in the universe, formed when the galaxy was young, perhaps only a few 100 million years after the Big Bang. These stars have orbits that take them far above and below the galactic disk, looping out into the halo and then plunging back down through the disk. These halo stars are time capsules, preserving information about the early universe. They're poor in heavy elements, containing mostly hydrogen and helium, because they formed before generations of stars had lived and died, producing the heavier elements through nuclear fusion and supernova explosions. By studying these stars, we can learn about the conditions in the early universe, about how the first galaxies formed, about the processes that shaped the cosmos. And some of these halo stars might have planets, old planets, ancient worlds that have existed for 10 billion years or more. What might we find on such planets? If life emerged there, it would have had twice as long to evolve as life on Earth. What forms might it take? What civilizations might have risen and fallen? What technologies might have been developed and forgotten? These are the kinds of questions that haunt astronomers who study the structure above and below the galactic plane. Because the universe is not just vast in space, it's vast in time. And the regions above and below the solar system are connected to that deep time, to the history of the galaxy, to the entire story of cosmic evolution. Let's think about supernova for a moment. Those catastrophic stellar explosions that outshine entire galaxies for a few weeks. Supernovae are not evenly distributed in the galaxy. They occur more frequently in the galactic plane, where most of the stars are. But the blast waves from supernova don't respect the plane. They expand in all directions, creating bubbles of hot gas that can extend hundreds of light years above and below the plane.
These supernova bubbles interact, merge, create a complex foam-like structure in the interstellar medium. The Sun is currently inside one of these bubbles, called the local bubble. It's a region about 600 light-years across, carved out by supernova explosions that occurred millions of years ago. The gas inside the local bubble is hot, about 1,000,000 degrees, and very thin, creating a relatively clear path for light from nearby stars. The walls of the local bubble, where the hot interior gas meets the cooler, denser gas of the surrounding interstellar medium, are sites of active star formation. New stars are being born there right now, condensing out of the compressed gas. These walls extend above and below the galactic plane, creating a three-dimensional structure that surrounds us. And the local bubble is not unique. There are many such bubbles in the galaxy, overlapping, merging, creating a complex structure that defies simple description. The space above and below the solar system is filled with these structures, invisible to the naked eye, but revealed by X-ray telescopes and radio telescopes, mapping the hot gas and the magnetic fields threading through it. Now let's consider something truly exotic: hypervelocity stars. These are stars moving so fast that they're escaping the galaxy entirely, traveling at speeds of 500 to 1,000 kilometers per second or more. They're being flung out of the galaxy, mostly from the galactic center, where close encounters with the supermassive black hole can accelerate stars to these incredible velocities. These hypervelocity stars are leaving the galactic disk, moving above and below it, heading out into the galactic halo and eventually into intergalactic space. Some of them might have planets. Imagine being on a planet orbiting a hypervelocity star, watching your galaxy recede behind you, knowing that you're being carried away from your cosmic home, destined to drift through the void between galaxies for billions of years. And if planets can be carried away by hypervelocity stars, could life be carried with them? Could civilizations exist on these wayward worlds, exiled from their galaxy, developing in isolation, creating cultures and technologies shaped by their unique situation? These are the kinds of speculative thoughts that emerge when we truly contemplate the structures above and below the solar system, because our cosmic neighborhood is not isolated. It's part of a vast, interconnected galaxy, and the galaxy itself is part of an even vaster universe. Let's talk about the solar apex and antipex, because these concepts help us understand our motion through the galaxy. The solar apex is the direction in the sky toward which the Sun is moving relative to nearby stars. Right now, it's in the constellation Hercules. The solar antipex is the opposite direction, the point we're moving away from, currently in the constellation Columba. As we move toward the solar apex, we're approaching stars in that direction and receding from stars in the opposite direction. This creates a pattern of motion in the sky, a subtle effect that can be measured by tracking stellar positions over many years. And this motion is important because it affects what we encounter above and below the solar system. The density of the interstellar medium varies depending on our location in the galaxy. As we move, we pass through denser and less dense regions. These variations affect the heliosphere, changing its size and shape. When we pass through denser regions, the heliosphere shrinks, allowing more cosmic rays to penetrate the inner solar system. This might affect Earth's climate, cloud formation,
and possibly even the rate of mutations in living organisms. Some scientists have proposed that the solar system periodically passes through the spiral arms of the galaxy, regions where star formation is more active and where the density of gas and dust is higher. These passages might trigger ice ages on Earth, increase comet impacts, and generally create more turbulent conditions in the solar system. The evidence is debated, but the idea is intriguing that events on Earth might be influenced by our position in the galaxy, by the structures above and below us on galactic scales. And then there's the cosmic microwave background, that faint glow of radiation left over from the Big Bang, filling the entire universe. The cosmic microwave background is almost perfectly uniform, the same temperature in all directions, with only tiny variations of 1 part in 100,000. But those tiny variations tell us about the structure of the early universe, about the seeds from which galaxies and galaxy clusters grew. Above and below the solar system, in every direction, the cosmic microwave background is always there, a reminder of the universe's origin, a signal from the earliest moments of time. We can't see it with our eyes. Its photons have too little energy. They're in the microwave part of the spectrum. But with the right instruments, we can detect it, map it, study it. And when we do, we see hints of the largest structures in the universe. The cosmic microwave background shows us the universe as it was 380,000 years after the Big Bang, when atoms first formed, and light could travel freely through space for the first time. The pattern of hot and cold spots in the cosmic microwave background corresponds to regions of slightly higher and lower density, which eventually collapsed under gravity to form the galaxies and galaxy clusters we see today. So, above and below the solar system, encoded in the cosmic microwave background, is the history of the universe itself. The structures we see around us today, the filaments and voids of the cosmic web, the galaxies and clusters, all of it traces back to those tiny variations in the early universe, amplified by billions of years of gravitational collapse and expansion. Let's think about the intergalactic medium, the gas that exists between galaxies. It's incredibly thin, less than 1 atom per cubic meter in many places, but it's there, filling the voids, connecting galaxies through a network of gaseous filaments. This gas is mostly hydrogen, left over from the Big Bang, plus a small amount of helium and traces of heavier elements forged in stars and expelled into the intergalactic medium by supernova explosions and galactic winds. The intergalactic medium above and below the solar system, far above and below the Milky Way, is part of the cosmic web. It's cold, only a few tens of thousands of degrees in some places, hot in others where it's been heated by shocks from galaxy mergers or by radiation from active galactic nuclei. Mapping the intergalactic medium is one of the challenges of modern astronomy, requiring sensitive observations of how light from distant quasars is absorbed as it passes through the gas.
This gas will eventually be pulled into galaxies by gravity, where it will fuel new generations of star formation. The intergalactic medium is the reservoir from which galaxies draw their raw material. It's the medium that connects all galaxies, making them part of a single interconnected system rather than isolated islands in the cosmos. And beyond the intergalactic medium, on the very largest scales, there's something even more mysterious: dark energy. Dark energy is the name we give to whatever is causing the universe's expansion to accelerate. About 5 billion years ago, the expansion of the universe, which had been slowing down due to gravity, began to speed up instead. Something is pushing the universe apart, overwhelming the attractive force of gravity on large scales. We don't know what dark energy is. We measure its effects, we can quantify how much of it there must be, about 68% of the universe's total energy density, but we don't understand its nature. Is it a property of space itself? A cosmological constant, as Einstein proposed? Is it a dynamic field, changing over time? Is it something even stranger, a sign that our understanding of gravity breaks down on the largest scales? Dark energy exists above and below the solar system, throughout all of space, at every point in the universe. It's not concentrated in any particular location. It's a property of the vacuum itself, or of space-time, or of something we haven't conceived of yet. And it's pulling the universe apart, making the voids larger, making galaxies move away from each other faster and faster. In the far future, trillions of years from now, dark energy will have pulled galaxies so far apart that each galaxy will be isolated, unable to see any others, surrounded by an ever-expanding void. The cosmic horizon, the distance beyond which light hasn't had time to reach us since the Big Bang, will shrink. Eventually, only the local group of galaxies, gravitationally bound together and resisting the expansion, will remain visible. The rest of the universe will have been carried beyond the horizon, forever unreachable. But that's the far future. For now, we live in an age where we can still see most of the universe, where the structures above and below the solar system are rich and complex and full of information. We live in a special time, a brief window in cosmic history when the universe is neither too young and simple nor too old and empty. Let's think about magnetic fields, because they're one of the most underappreciated aspects of what lies above and below the solar system. Magnetic fields are everywhere in the cosmos. Earth has a magnetic field generated by the motion of molten iron in its core. The Sun has a magnetic field generated by the motion of plasma in its interior. Jupiter has the strongest planetary magnetic field in the solar system. Even Mars had a magnetic field in the past, though it's gone now, leaving Mars vulnerable to the solar wind, which has slowly stripped away most of its atmosphere over billions of years. But magnetic fields extend far beyond planets and stars. The galaxy itself has a magnetic field threading through the interstellar medium, aligned with the galactic spiral arms. This galactic magnetic field is weak, about 1/1,000,000th of Earth's magnetic field strength, but it extends over vast distances, shaping the motion of charged particles, influencing cosmic rays, affecting star formation. Above and below the galactic plane, the magnetic field is more disordered, more tangled, but it's still there. It's one of the invisible structures that shape the galaxy, that determine how matter moves and how energy is transported. Without magnetic fields, the galaxy would look very different. Stars would form at different rates. Cosmic rays would propagate differently. The entire structure of the interstellar medium would be altered. Magnetic fields also create phenomena like synchrotron radiation, the glow produced by when electrons spiral around magnetic field lines at near light speed. This radiation is visible at radio wavelengths, creating the beautiful images we see of supernova remnants, pulsar wind nebulae, and active galactic nuclei. These objects shine brightly in radio light, revealing the magnetic structures within them, the fields that channel energy and accelerate particles to extreme velocities. And magnetic fields might be crucial for life. Earth's magnetic field protects us from the solar wind and cosmic rays, preserving our atmosphere, making the surface a safer place for life. Without a magnetic field, Earth might have ended up like Mars, cold and dry and nearly airless. So when we think about habitable planets around other stars, we need to think about magnetic fields too. A planet in the habitable zone of its star might still be uninhabitable if it lacks a magnetic field to protect it. This means that above and below the solar system, the magnetic structures of the galaxy might influence the distribution of life in the universe. Regions with stronger magnetic fields, regions with more protection from cosmic rays, might be more favorable for life. The galactic halo, with its weaker magnetic field and higher cosmic ray flux, might be less hospitable. These are factors we're only beginning to consider as we think about where to search for life beyond Earth. Let's consider the concept of the galactic habitable zone, the region in a galaxy where conditions are most favorable for life. Too close to the galactic center, and the density of stars is too high, leading to frequent supernova explosions, stellar collisions, and intense radiation that might sterilize planets. Too far from the galactic center, and there aren't enough heavy elements to form rocky planets, because heavy elements are produced by stars, and the outer regions of galaxies have lower star formation rates. The Sun is in a relatively sweet spot, about 26,000 light-years from the galactic center, in a region where heavy elements are abundant, but supernova explosions are relatively infrequent. And this location affects what lies above and below us. Above and below the solar system, at our galactic radius, the environment is relatively calm, relatively safe, relatively conducive to the long-term stability that life requires. But this is changing as we orbit the galaxy. We move through spiral arms, regions where star formation is more active, where supernova explosions are more common. These passages might create periods of higher risk, times when Earth is bombarded by cosmic rays, when comets are perturbed from the Oort cloud, when the environment becomes more chaotic. Some scientists have speculated that these passages correlate with mass extinction events in Earth's history, though the evidence is far from conclusive. So the structures above and below the solar system, the position of the Sun in the galaxy, the density of the interstellar medium, the strength of the magnetic field, all of these factors might have influenced the history of life on Earth. We are not separate from our cosmic environment. We are part of it, shaped by it, dependent on it. Let's think about the future of space exploration, because as we venture out from Earth, we'll be exploring these regions above and below the solar system directly. Missions to the outer planets, to the Kuiper Belt, to interstellar space, all of them will encounter the structures we've been discussing. New Horizons, the spacecraft that flew by Pluto in 2015, is now heading into the Kuiper Belt, studying distant objects, measuring the environment beyond Neptune. It's currently about 60 astronomical units from the Sun and will continue transmitting data until the 2030s if all goes well. After that, it will coast silently through the outer solar system, passing through the heliopause sometime in the 2040s or 2050s, joining Voyager 1 and Voyager 2 in interstellar space.
Future missions might explore even farther. There are proposals for missions to the Solar Gravitational Lens Focus, a point about 550 astronomical units from the Sun, where the Sun's gravity bends light from distant objects so strongly that it acts like a giant telescope lens. A spacecraft positioned at that distance could use the Sun as a lens to image distant stars and exoplanets with unprecedented resolution, potentially even detecting signs of life on planets hundreds of light-years away. But reaching 550 astronomical units is a challenge. It would take decades, even with advanced propulsion systems. And at that distance, the spacecraft would be well into the region we've been discussing, the realm where the solar system blurs into interstellar space, where the Oort cloud is spread around us, where the Sun's influence is barely distinguishable from that of other stars. Imagine being on such a spacecraft, looking back at the Sun, seeing it as just another bright star in the sky, looking out at the Oort cloud objects drifting past, ancient relics from the formation of the solar system, looking toward the center of the galaxy, seeing the glow of billions of stars, looking up and down, above and below the galactic plane, contemplating the vast structures that surround us. This is the future of exploration, not just visiting planets, but venturing into the true depths of the solar system, into the regions we've been discussing, the spaces above and below that hold so many mysteries. And perhaps, someday, we'll go even farther. There are concepts for interstellar missions, spacecraft that could reach other stars within a human lifetime or less. These missions would require new technologies, perhaps fusion rockets, perhaps antimatter drives, perhaps light sails pushed by powerful lasers. But they're not impossible. They're engineering challenges, not violations of physics. If we build such ships, if we send them to nearby stars, they'll pass through the region where the Oort clouds of our Sun and those stars overlap. They'll see objects from both systems, perhaps indistinguishable from each other. They'll experience the transition from one star's heliosphere to another, from one star's domain to another. And when they arrive at another star, they'll find what lies above and below that star's system. Will it have an Oort cloud like ours? Will it have planets? Will those planets have life? These are questions we can only answer by going there, by seeing for ourselves, by exploring directly. But even if we never leave the solar system, even if we never build interstellar ships, we can still study what lies above and below us through observation. Every telescope we build, every detector we deploy, every astronomical survey we conduct adds to our understanding of the cosmic environment we inhabit. The James Webb Space Telescope, launched in 2021, is currently observing the universe in infrared light, piercing through dust clouds, seeing the first galaxies that formed after the Big Bang, studying exoplanet atmospheres, revealing details that previous telescopes couldn't see. And much of what it observes is above and below us in three-dimensional space. Objects at different distances, at different positions relative to the galactic plane, giving us a three-dimensional map of the universe. Ground-based telescopes are getting larger and more sophisticated. The extremely large telescope, currently under construction in Chile, will have a mere 39 meters in diameter when completed. It will be able to directly image exoplanets, study the atmospheres of rocky worlds, search for signs of life, and observe objects in the distant universe with unprecedented clarity. These telescopes will help us understand what lies above and below the solar system by observing similar structures around other stars, by studying the galactic halo in detail, by mapping the intergalactic medium, by probing the nature of dark matter and dark energy. Every observation teaches us something new, challenges our assumptions, forces us to revise our models. And there are mysteries to still solve, questions we haven't answered. The nature of dark matter, the nature of dark energy, the fate of the universe, the prevalence of life, the possibility of intelligent civilizations. These are big questions, profound questions, questions that touch on philosophy and meaning and our place in the cosmos. What does it mean to be human in a universe so vast, so complex, so filled with structures that dwarf our comprehension? What does it mean to live on a tiny planet, orbiting an ordinary star, in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies? Some people find these thoughts depressing, nihilistic, proof that we're insignificant. But others find them exhilarating, inspiring, a reminder of how much there is to explore and understand. We are part of this vast cosmos. We are made of atoms forged in stars. We are the universe becoming aware of itself, contemplating its own existence, asking questions about its nature and origin. And what lies above and below the solar system, all those structures we've discussed, the Oort cloud, the heliosphere, the galactic halo, the cosmic web, all of it is part of our cosmic heritage. We are not isolated from these structures. We are embedded in them. They shape our existence. They influence our planet. They connect us to the rest of the universe. The Oort cloud, remember, contains the leftover material from the formation of the solar system. Those icy objects are made of the same stuff that made the planets, the same stuff that made Earth, the same stuff that made us. The water in your body might have been delivered to Earth by comets from the Oort cloud, crashing into the young Earth billions of years ago, filling the oceans, making life possible. The heliosphere protects us from cosmic rays, particles accelerated by supernova explosions, events that also created the heavy elements in our bodies. The iron in your blood was forged in a dying star, ejected into space by a supernova explosion, incorporated into the cloud of gas and dust that would eventually form the sun and the planets. The galactic halo above and below us contains stars that have orbited the galaxy for 10 billion years or more. Those stars have seen the Milky Way evolve, seen it merge with smaller galaxies, seen it transform from a small, irregular galaxy into the grand spiral we know today. Those stars are witnesses to cosmic history, and by studying them, we learn our history. The cosmic web, the largest structure in the universe, determines where galaxies form, where clusters assemble, where voids expand. The Milky Way is part of a filament in this web, and that filament connects us to other galaxies, other clusters, other regions of the universe. We are not alone. We are part of a vast interconnected system. And dark energy, mysterious as it is driving the future evolution of the universe. It's pulling space apart, accelerating the expansion, determining the ultimate fate of everything. In the far future, dark energy will have isolated our local group of galaxies from all others. But that's trillions of years away. For now, we live in a universe that's still young, still evolving, still full of structure and complexity.
What lies above and below the solar system is not just empty space. It's a rich, layered, complex environment. It's the Oort cloud, a shell of icy objects surrounding us at vast distances. It's the heliosphere, the protective bubble created by the solar wind. It's the scattered disk, the region of strange orbits and mysterious objects that hint at Planet 9. It's the galactic halo, populated by old stars and dominated by dark matter. It's the local bubble, carved out by ancient supernova explosions. It's the intergalactic medium, the gas that connects galaxies. It's the cosmic web, the largest structure in the universe. It's dark energy, pulling everything apart. It's magnetic fields, threading through space, invisible but influential. It's cosmic rays, high-energy particles from distant cataclysms. It's all of these things and more. Every time we look up, whether with our eyes or with telescopes, whether in visible light or radio waves or X-rays or gravitational waves, we're seeing through these layers, these structures, these regions above and below us. We're seeing the universe not as it is now, but as it was when the light left those distant objects. Because light travels at a finite speed, and the universe is vast. When we look at the Andromeda galaxy, 2.5 million light-years away, we're seeing it as it was 2.5 million years ago, when our ancestors were just beginning to use stone tools. When we look at distant galaxies billions of light-years away, we're seeing them as they were in the early universe, when they were young and actively forming stars, very different from the mature galaxies we see nearby. So, above and below the solar system, in every direction, we're looking into the past. The farther we look, the farther back in time we see. This is one of the most beautiful aspects of astronomy. We can study the history of the universe directly by observing distant objects. We can see how galaxies evolve, how stars form and die, how the universe has changed over billions of years. And this brings us to a philosophical point, a reflection on what it all means. We live in a remarkable time in cosmic history. The universe is 13.8 billion years old, and we exist in an era when stars are still forming, when galaxies are still evolving, when the cosmic web is still growing. In the far future, star formation will slow and eventually stop as the universe runs out of gas. Existing stars will die and no new ones will be born. The universe will gradually darken, filled only with the fading embers of dead stars, white dwarfs and neutron stars and black holes. But that's trillions of years in the future. For now, we live in a vibrant, energetic universe, full of light and structure and complexity. And we have the privilege of being conscious observers, able to study this universe, to understand it, to appreciate its beauty and its mysteries. What lies above and below the solar system is ultimately the cosmos itself. It's the galaxy we inhabit, the group of galaxies we're part of, the supercluster we belong to, the cosmic web we're embedded in, the universe as a whole. And all of it, every part of it, from the Oort cloud to the edge of the observable universe, is connected. Not just physically through gravity and magnetic fields and the exchange of matter and energy, but conceptually, as parts of a single integrated system. We are not separate from this system, we are part of it. Our atoms came from stars. Our planet formed from the debris of the solar nebula. Our evolution was shaped by impacts from comets and asteroids, by climate changes influenced by orbital variations, by extinction events that cleared ecological niches and allowed new forms of life to arise. And as we contemplate what lies above and below the solar system, as we marvel at the Oort cloud and the heliosphere and the galactic halo and all the rest, we're really contemplating our own place in the universe. We're asking, where did we come from? What are we made of? What forces shaped our world? What is our relationship to the cosmos? These are ancient questions asked by every culture throughout human history. But now, for the first time, we have the tools to answer them scientifically. We have telescopes that can see to the edge of the observable universe. We have spacecraft exploring the outer solar system. We have theoretical models that describe the evolution of the cosmos from the Big Bang to the present day. And what we've learnt is humbling and awe-inspiring in equal measure. We've learnt that we're tiny, insignificant on cosmic scales, inhabitants of a small planet orbiting an ordinary star in an ordinary galaxy. But we've also learnt that we're extraordinary, the product of billions of years of cosmic evolution, made of atoms forged in the hearts of stars, possessing consciousness and intelligence and the ability to understand the universe we inhabit. What lies above and below the solar system is, in a sense, our extended body. The Oort cloud is our outermost layer, the boundary between our star system and the galaxy. The heliosphere is our protective shell, shielding us from the harshness of interstellar space. The galactic halo is our cosmic neighborhood, the region we travel through as we orbit the galactic center. The cosmic web is our address in the universe, locating us within the largest structures that exist. And all of it, every part of it, from the Oort cloud to the edge of the observable universe, is connected. Not just physically through gravity and magnetic fields and the exchange of matter and energy, but conceptually as parts of a single integrated system. We are not separate from this system, we are part of it. Our atoms came from stars. Our planet formed from the debris of the solar nebula. Our evolution was shaped by impacts from comets and asteroids, by climate changes influenced by orbital variations, by extinction events that cleared ecological niches and allowed new forms of life to arise. And as we contemplate what lies above and below the solar system, as we marvel at the Oort cloud and the heliosphere and the galactic halo and all the rest, we're really contemplating our own place in the universe. We're asking, where did we come from? What are we made of? What forces shaped our world? What is our relationship to the cosmos? These are ancient questions asked by every culture throughout human history. But now, for the first time, we have the tools to answer them scientifically.
We have telescopes that can see to the edge of the observable universe. We have spacecraft exploring the outer solar system. We have theoretical models that describe the evolution of the cosmos from the Big Bang to the present day. And what we've learned is humbling and awe-inspiring in equal measure. We've learned that we're tiny, insignificant on cosmic scales, inhabitants of a small planet orbiting an ordinary star in an ordinary galaxy. But we've also learned that we're extraordinary, the product of billions of years of cosmic evolution, made of atoms forged in the hearts of stars, possessing consciousness and intelligence and the ability to understand the universe we inhabit. What lies above and below the solar system is, in a sense, our extended body. The Oort cloud is our outermost layer, the boundary between our star system and the galaxy. The heliosphere is our protective shell, shielding us from the harshness of interstellar space. The galactic halo is our cosmic neighborhood, the region we travel through as we orbit the galactic center. The cosmic web is our address in the universe, locating us within the largest structures that exist. And all of it, every part of it, from the Oort cloud to the edge of the observable universe, is connected. Not just physically, through gravity and magnetic fields and the exchange of matter and energy, but conceptually, as parts of a single integrated system. We are not separate from this system, we are part of it. Our atoms came from stars. Our planet formed from the debris of the solar nebula. Our evolution was shaped by impacts from comets and asteroids, by climate changes influenced by orbital variations, by extinction events that cleared ecological niches and allowed new forms of life to arise. And as we contemplate what lies above and below the solar system, as we marvel at the Oort cloud and the heliosphere and the galactic halo and all the rest, we're really contemplating our own place in the universe. We're asking, where did we come from? What are we made of? What forces shaped our world? What is our relationship to the cosmos? These are ancient questions asked by every culture throughout human history. But now, for the first time, we have the tools to answer them scientifically. We have telescopes that can see to the edge of the observable universe. We have spacecraft exploring the outer solar system. We have theoretical models that describe the evolution of the cosmos from the Big Bang to the present day. And what we've learned is humbling and awe-inspiring.
On these timescales, human civilization is a brief flicker. All of recorded history, all of human achievement, all of our art and science and philosophy has occurred in the last few thousand years. That's less than 1/1,000,000th of the age of the universe. We're newcomers, late arrivals to the cosmic story. But we're here now. We're conscious. We're aware. We're asking questions. And that matters. That's significant. Because as far as we know, we might be the only beings in the universe capable of understanding the universe, of contemplating what lies above and below the solar system, of appreciating the vast structures and deep time that characterize the cosmos. This imposes a kind of responsibility. Not a responsibility imposed by anyone else, but one we impose on ourselves. If we're the universe's way of understanding itself, then we have an obligation to preserve that understanding, to continue exploring, to keep asking questions, to ensure that consciousness and intelligence don't disappear from the cosmos. This means taking care of our planet. It means avoiding self-destruction through war or environmental catastrophe. It means eventually spreading beyond Earth, establishing ourselves elsewhere in the solar system, and perhaps beyond, so that we're not dependent on a single planet for survival. And it means continuing to study what lies above and below the solar system, continuing to map the Oort cloud, continuing to search for Planet 9, continuing to explore the heliosphere and the galactic halo and the cosmic web. Because in doing so, we are ensuring that the universe remains understood, that the consciousness that arose in this tiny corner of the cosmos persists and flourishes. What lies above and below the solar system, then, is not just a scientific question. It's a philosophical question. It's about who we are, where we came from, and where we're going. It's about our relationship to the cosmos, our place in the vast sweep of space and time. And the answer to this question is still being written. With every new observation, with every new discovery, with every new mission we launch, we add another piece to the puzzle. We refine our understanding. We reveal new mysteries. The Oort cloud might be larger than we think. Planet 9 might exist, or it might not. The heliosphere might change shape as we move through different regions of the galaxy. The galactic halo might contain exotic forms of dark matter that interact in unexpected ways. The cosmic web might have features we haven't noticed yet. We don't know. And that's exciting. That's what makes science thrilling. We're exploring terra incognita, cosmic regions that no one has mapped in detail, structures that challenge our understanding, phenomena that push the boundaries of what we thought was possible. And as we explore, as we learn, as we discover, we're writing a new chapter in the human story. We're transforming ourselves from a species confined to a single planet into a spacefaring civilization, aware of its cosmic context, ready to take its place in the galaxy. What lies above and below the solar system is, ultimately, our future. It's the realm we'll explore in the coming centuries and millennia. It's the region where we might establish outposts, build telescopes, send probes, perhaps even encounter other civilizations if they exist. It's the frontier, the next horizon, the great unknown. And it's waiting for us, patient and silent, ready to reveal its secrets to those brave enough to venture into the darkness, to leave behind the familiar warmth of the inner solar system, to journey into the cold and vast regions beyond. This is what lies above and below the solar system. Not just ice and rock and dust, not just empty space and distant stars, but possibility, mystery, wonder. The promise of discovery, the challenge of the unknown, the invitation to explore, to understand, to become something more than we are. And perhaps someday, when we've mapped every object in the Oort cloud, when we've found Planet 9 or proved it doesn't exist, when we've sent probes throughout the heliosphere and beyond, when we've unraveled the mysteries of dark matter and dark energy, when we understand the cosmic web in all its complexity, perhaps then we'll look back at this moment, this time when we were just beginning to understand what lay above and below our cosmic neighborhood, and we'll marvel at how far we've come. But that day is far in the future. For now, we stand at the threshold, gazing up and down, contemplating the vast structures that surround us, asking questions, seeking answers, driven by the same curiosity that has always defined our species. What lies above and below the solar system? Everything. What lies above and below the solar system? Everything. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting, above and below, around us, through us. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting, above and below, around us, through us. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting, above and below, around us, through us. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting, above and below, around us, through us. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting, above and below, around us, through us. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting, above and below, around us, through us. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting, above and below, around us, through us. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting, above and below, around us, through us. What lies above and below the solar system? Everything. The past and the future. Our origins and our destiny. The story of the cosmos and our place within it. The known and the unknown. The discovered and the yet to be discovered. It's all there, waiting.
Let me take you deeper still into realms we haven't yet explored. Because there's something extraordinary happening right now, at this very moment, as you read these words. Something is passing through you, through your body, through the Earth, through the entire solar system. Trillions upon trillions of particles, ghostly and nearly undetectable, streaming from above and below at nearly the speed of light. They're called neutrinos. These particles are so bizarre, so contrary to everyday experience, that they seem almost magical. A neutrino could pass through a light year of solid lead and never interact with a single atom. They're born in the heart of the sun,
created by nuclear fusion reactions, and they stream outward in all directions. 60 billion neutrinos from the sun pass through every square centimeter of your body every single second. 60 billion! Every second. You never feel them. They leave no trace. They simply pass through as if you weren't there. But the solar neutrinos are just the beginning. Far above and below the solar system, in the depths of space, other sources are producing neutrinos. Supernova explosions create torrents of them, so intense that a nearby supernova could be detected by the neutrino burst alone hours before the light reaches us. Active galactic nuclei, those monster black holes in the centers of distant galaxies, produce neutrinos as they devour matter. Cosmic ray collisions in the atmosphere of Earth create neutrinos. The Big Bang itself created a background of neutrinos that still fills the universe, though they're now so low in energy that we can't detect them. What does this mean? It means that right now, passing through the space above and below the solar system is information. Invisible information, messages from the heart of the sun, from distant stellar explosions, from the edge of black holes, from the birth of the universe itself. We're bathed in these messages constantly, swimming in an ocean of neutrinos that connects us to every energetic event in the cosmos. And we've only recently learned to read these messages. Neutrino detectors, built deep underground or deep under ice to shield them from other particles, are beginning to catch these elusive messengers. In 1987, when a supernova exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, neutrino detectors on Earth caught the burst. 20 neutrinos. Out of the countless trillions that passed through Earth, only 20 interacted with the detector. But those 20 neutrinos told us about the collapse of a massive star's core, about the formation of a neutron star or black hole, about conditions so extreme that matter is compressed to nuclear densities. Think about that. Light from the supernova took 168,000 years to reach us. Those photons, traveling at the speed of light, were on a journey that began before modern humans left Africa. And yet the neutrinos carried information about the supernova's core, the innermost region where the explosion began. Information that light couldn't carry because light was trapped in the outer layers of the star for hours before breaking free. Neutrinos are cosmic X-rays, letting us see inside opaque objects, revealing hidden processes. And they're everywhere, above and below the solar system, creating an invisible landscape of information that we're only beginning to map. But there's another invisible landscape, equally profound: gravitational waves. These are ripples in space-time itself, created when massive objects accelerate. When two black holes spiral into each other and merge, they shake space-time, sending waves propagating outward at the speed of light. When neutron stars collide, they create gravitational waves. Even the Big Bang itself created a background of gravitational waves that might still be detectable, encoded in the polarization of the cosmic microwave background. We detected gravitational waves for the first time in 2015. Two black holes, each about 30 times the mass of the Sun, merged about 1.3 billion light-years away. The gravitational waves from this merger passed through Earth, compressing and stretching space-time by less than the width of a proton, less than the width of a subatomic particle. And yet the LIGO detectors caught them, measured them, confirmed that Einstein's century-old prediction was correct. Since then, we've detected dozens of these events: black hole mergers, neutron star mergers, exotic events that don't fit our expectations, and each detection tells us something new about what lies above and below the solar system, because these gravitational waves pass through everything. They're not blocked by matter.
They don't scatter or absorb. They simply pass through, carrying pristine information about the events that created them. This means that above and below the solar system, space-time itself is constantly vibrating, constantly rippling with gravitational waves from countless sources throughout the universe. Most of them are too weak to detect, but they're there. A cosmic symphony of space-time oscillations, each wave carrying information about some violent event somewhere in the cosmos. And here's something that should make you pause. Gravitational waves are not just signals. They're actual distortions in the fabric of reality. When a gravitational wave passes through you, you are literally stretched and compressed, your body oscillating in sync with the wave. The distances between atoms in your body change. Not by much, less than the width of a subatomic particle, but they change. You are being constantly reshaped by gravitational waves from distant cosmic events, connected to those events through the geometry of space-time itself. Now let's talk about something even stranger. Time. Because time doesn't flow uniformly throughout the solar system, above and below it, or anywhere in the universe. Time is relative, flexible, dependent on gravity and motion. This is Einstein's theory of relativity, proven countless times fundamental to our understanding of the cosmos. Near massive objects, time runs slower. This isn't just theory. GPS satellites have to correct for this effect. Time runs slightly faster in orbit than on Earth's surface because Earth's gravity is weaker up there. If the satellites didn't account for this, GPS navigation would become inaccurate within hours. Now extend this to cosmic scales. Near the supermassive black hole at the center of the Milky Way, time runs much slower than it does here in our location. An observer near the black hole would see the rest of the galaxy moving in fast forward. An observer far from the black hole would see someone near it moving in slow motion. This means that above and below the solar system, in regions with different gravitational environments, time itself is flowing at different rates. There's no universal now in the cosmos. Events that are simultaneous for one observer are not simultaneous for another. The universe doesn't have a single timeline, but countless timelines, interweaving, overlapping, each dependent on the observer's motion and location. And if you move fast enough, time slows down for you relative to stationary observers. A spacecraft traveling at 90% the speed of light would experience time passing about twice as slowly as observers on Earth. Travel for 10 years at that speed, and 20 years would pass on Earth. This is time dilation, and it's real, measured, verified. What does this mean for the structures above and below the solar system? It means that different regions are not just separated in space, but also experiencing time differently. A civilization near the galactic center would age more slowly than us. Clocks in the galactic halo, far from massive objects, would tick faster than clocks in the galactic disk.
The universe is not a static stage where events unfold. It's a dynamic, flexible, interconnected spacetime where past, present, and future blur together, where distances and durations depend on your perspective, where the very fabric of reality is shaped by mass and energy. Let's think about black holes for a moment. Not the supermassive one at the galactic center, but stellar mass black holes, the remnants of massive stars that have collapsed. The Milky Way contains millions of these objects, perhaps tens of millions, scattered throughout the galaxy. Some are in the galactic disk, some in the halo, above and below the plane where the sun orbits. Most of these black holes are invisible, dark, silent, detectable only by their gravitational effects on nearby objects. But occasionally, one of them captures a companion star, stripping gas from it, forming an accretion disk of superheated material spiraling into the black hole. These systems shine brightly in X-rays, revealing the black hole's presence. And there are stranger objects still. Magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's. These objects occasionally produce bursts of gamma rays and X-rays so intense that they can affect Earth's atmosphere from thousands of light-years away. In 2004, a magnetar named SGR 1806-20 erupted, releasing more energy in 1/10 of a second than the Sun releases in 100,000 years. The burst hit Earth's atmosphere, ionizing it, temporarily disturbing radio communications. This was from an object 50,000 light-years away on the opposite side of the galaxy. Imagine if a magnetar existed closer, above or below the solar system in the galactic halo. Its bursts could affect our planet regularly, increasing radiation levels, potentially impacting life. We're fortunate that the nearest known magnetar is safely distant, but there might be others we haven't discovered, lurking in the darkness above or below the galactic plane. Then there are rogue planets, worlds that don't orbit any star, ejected from their home systems by gravitational interactions, now drifting through the galaxy alone. Studies suggest there might be billions of these worlds in the Milky Way, perhaps more rogue planets than stars. They're nearly impossible to detect, cold and dark, visible only when they pass in front of a background star and briefly magnify its light through gravitational lensing. These rogue planets exist above and below the solar system, throughout the galactic halo and disk, wandering eternally through the darkness. Some of them might be Earth-sized. Some might even have enough internal heat to have subsurface oceans, where life could potentially exist, cut off from starlight, surviving on geological energy alone. What would it be like on such a world? Eternal night, no sun, no seasons, no day or night cycle. The sky would be black, filled with stars, but no bright point dominating the view. Any life that evolved there would be utterly unlike life on Earth, adapted to permanent darkness, perhaps clustered around volcanic vents or radioactive heat sources, never knowing that most worlds orbit stars, never seeing a sunrise or sunset. And some of these rogue planets might have been ejected from the solar system itself, billions of years ago, during the chaotic early period when planet formation was still underway. Computer simulations suggest that the young solar system might have had additional planets, super-Earths or ice giants, that were flung out by gravitational interactions with Jupiter. These lost siblings of Earth might still exist, somewhere in the galaxy, carrying within them clues about the solar system's formation. Could we ever find them? Could we identify a rogue planet as once belonging to our system? Maybe, if we could analyze its composition, compare it to objects in the solar system, look for matching chemical signatures. But the chances of finding such a world are astronomically small. Space is vast, and rogue planets are dim and distant. Let's shift perspective and think about energy. Not just the energy of stars and black holes, but the energy of empty space itself. Because empty space is not truly empty. Quantum mechanics tells us that the vacuum is seething with activity, with virtual particles constantly appearing and disappearing, with fields fluctuating at the smallest scales. This vacuum energy, also called zero-point energy, is real. We can measure it. The Casimir effect, where two metal plates placed very close together in a vacuum experience a force pushing them together, is caused by vacuum energy. The space between the plates contains fewer virtual particles than the space outside, creating a pressure difference. Now scale this up. The vacuum above and below the solar system, throughout the entire universe, contains this energy, and not just a little energy. The density of vacuum energy might be enormous, contributing to the mysterious dark energy that's accelerating the universe's expansion. Think about what this means. Empty space, the void between stars, the gaps between galaxies, all of it is filled with energy. Space itself has mass, has pressure, has properties. The vacuum is not nothing. It's something. Something active and dynamic. Something that affects the evolution of the entire universe. And this vacuum is unstable, at least in theory. Our universe might not be in its lowest energy state. We might be in a metastable vacuum, a false vacuum, sitting in a local minimum of energy, like a ball balanced on a hilltop. And if that's true, then quantum tunneling could create a bubble of true vacuum, a region where space falls to its actual lowest energy state, releasing enormous energy in the process. This bubble would expand at the speed of light, transforming everything it touches. The laws of physics inside the bubble might be different. Particles might have different masses. Atoms might not be stable. Everything would be destroyed and remade according to new rules. Has this happened already somewhere in the universe above and below the solar system? Is there a bubble of true vacuum expanding toward us from some distant point? An invisible wall of transformed space-time rushing through the cosmos at light speed, impossible to detect until the moment it arrives? Probably not. The universe seems stable. If vacuum decay were common, we'd expect to see evidence of it. But the possibility exists, a reminder that even empty space, even the vacuum, is not truly understood, not truly tame, not truly safe.
Let's think about horizons, not the horizon you see on Earth where the land meets the sky, but cosmic horizons, boundaries beyond which we cannot see or communicate. The particle horizon, also called the cosmological horizon, is the distance beyond which light hasn't had time to reach us since the Big Bang. Currently, this horizon is about 46 billion light-years away in all directions. Beyond that distance, there is more universe, perhaps infinite universe, but we can't see it because light from there hasn't reached us yet. This means that above and below the solar system, in every direction, there's a sphere beyond which we are permanently isolated. We can never receive signals from beyond that sphere. We can never visit those regions. They are forever cut off from us, separate universes in a sense, even though they're part of the same physical universe. And this horizon is not fixed. It's expanding as the universe ages, as light from more distant regions has time to reach us. But it's expanding slower than the universe itself, because the universe's expansion is accelerating due to dark energy. Eventually, the horizon will stop expanding and begin to shrink. Distant galaxies will cross beyond it, disappearing from view forever, their light stretched into invisibility by the expansion of space. Billions of years from now, observers in the Milky Way will see a much emptier universe. Most galaxies will have disappeared beyond the horizon. Only the local group, gravitationally bound together and resisting the expansion, will remain visible. The night sky will be darker, lonelier, containing far fewer galaxies than we see now. And there are other horizons. The event horizon of a black hole, the boundary beyond which nothing can escape, not even light. Cross that boundary and you're doomed to fall into the singularity at the center, crushed to infinite density, destroyed completely. From the perspective of an outside observer, you never quite cross the horizon. Time dilation freezes you at the edge, your image fading and reddening but never disappearing. But from your perspective, you cross smoothly, seeing nothing special at the horizon itself, only realizing your fate when you try to turn around and find you can't. Black holes above and below the solar system have these horizons, pockets of space-time from which no information can escape, regions that are effectively deleted from the universe, gone forever. Except they're not entirely gone because black holes evaporate through Hawking radiation, slowly losing mass, eventually disappearing completely. But this process takes an inconceivably long time. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate, far longer than the current age of the universe.
Now think about the Roche limit, another kind of horizon, a boundary around massive objects where tidal forces become so strong that they tear apart anything that crosses it. Every planet, every star, every black hole has a Roche limit. Get too close, and you're shredded. The Sun's Roche limit for Earth-like objects is about 550,000 kilometers from its center. Inside that distance, Earth would be torn apart by tidal forces, ripped into a ring of debris. This is what happened to the object that used to orbit Saturn before it was destroyed, creating Saturn's magnificent rings. Are there objects above and below the solar system approaching their Roche limits? Probably. Binary stars orbiting each other closely, gas giant planets spiraling into their stars, asteroids venturing too near Jupiter. The universe is full of objects dancing with destruction, balanced on the edge of these invisible boundaries. Let's talk about the interstellar medium in more detail, because it's more complex than just thin gas. The interstellar medium has structure, layers, phases, each with different properties. The cold neutral medium, where hydrogen atoms exist at temperatures around 100 degrees above absolute zero. The warm neutral medium, where temperatures reach thousands of degrees. The warm ionized medium, heated by stellar radiation. The hot ionized medium, carved out by supernova explosions, with temperatures reaching millions of degrees. Above and below the solar system, these phases coexist, interwoven, creating a multi-phase interstellar environment. We're currently in the local bubble, a region of hot ionized medium surrounded by denser regions of cold and warm medium. As the Sun orbits the galaxy, we pass through these different phases, exposing the solar system to varying conditions. When we pass through cold, dense clouds, the heliosphere shrinks. More cosmic rays penetrate the inner solar system. The rate of supernova explosions nearby might increase because cold clouds are where stars form, and massive stars that form there will explode as supernovae within a few million years. Some scientists have proposed that passages through dense interstellar clouds might trigger ice ages on Earth, though the mechanism is uncertain. The increased cosmic ray flux might seed cloud formation in Earth's atmosphere, reflecting more sunlight, cooling the planet. Or the denser interstellar medium might compress the heliosphere so much that the outer planets become exposed to interstellar radiation, creating unusual heating patterns that somehow affect Earth's climate.
The evidence is controversial, debated, not yet conclusive. But the idea is fascinating, that Earth's climate, and therefore the evolution of life, might be influenced by interstellar conditions, by the structures above and below the solar system on galactic scales. And the interstellar medium is not just passive gas. It's threaded with magnetic fields, turbulent, chaotic, filled with shock waves from supernova explosions, sculpted by stellar winds, shaped by spiral density waves as they propagate through the galaxy. Spiral density waves. Let's linger on this concept, because it's one of the most beautiful aspects of galactic structure. The spiral arms we see in galaxies like the Milky Way are not fixed structures. They're waves, patterns that rotate through the galaxy, compressing gas as they pass, triggering star formation. The stars themselves are not moving with the spiral arms. Instead, stars enter a spiral arm, slow down as they pass through the denser region, then speed up as they exit, like cars entering and leaving a traffic jam. The spiral pattern persists, even though the individual stars and gas clouds are constantly flowing through it. Right now, the Sun is between spiral arms, in a region called the Orion Spur, a minor arm, or perhaps just a bridge between the Perseus and Sagittarius arms. In about 50 million years, we'll enter the Perseus arm, a denser region with more star formation, more supernovae, potentially more cosmic ray flux and interstellar dust. What will that mean for Earth? Will it affect our climate?
our biosphere? Our evolution? These are questions we're only beginning to ask, connections we're only starting to explore. The structures above and below the solar system, the galactic environment we travel through, might shape life on Earth in ways we haven't fully recognized. And there are stranger things still in the interstellar medium. Molecules. Complex organic molecules, the building blocks of life, floating between the stars. Astronomers have detected more than 200 different molecules in interstellar space, including amino acids, sugars, alcohols, and other compounds relevant to biology. Where do these molecules come from? Some form on the surfaces of dust grains, where atoms can meet and bond in the cold of space. Some are ejected by dying stars, created in the outflows and winds from red giants and planetary nebulae. Some might even form in the atmospheres of planets and be carried into space by impacts or atmospheric escape. This means that above and below the solar system, the interstellar medium is seasoned with organic chemistry, with the ingredients for life distributed throughout the galaxy. When new stars form, when their planets coalesce from the surrounding disk of gas and dust, these organic molecules are incorporated into the worlds being born. Life on Earth might have been seeded by molecules from interstellar space, complex organic compounds that formed between the stars and were delivered to the young Earth by comets and asteroids. We might all be children of the interstellar medium, constructed from materials that drifted through the galaxy before the solar system even existed. And if that's true here, it's true everywhere. Every star, every planet inherits chemistry from the interstellar medium. The same molecules exist around other stars, in other planetary systems, throughout the galaxy. The ingredients for life are universal, distributed everywhere, suggesting that life itself might be common, perhaps even inevitable, given the right conditions. Let's think about stellar populations, because they tell us about the history written in the structures above and below the solar system. Astronomers divide stars into populations based on their age and composition. Population 1 stars are young, metal-rich, found primarily in the galactic disk, orbiting in neat circles aligned with the galaxy's rotation. The Sun is a population 1 star, about 4.6 billion years old, middle-aged, containing about 2% of its mass in elements heavier than helium. Population 2 stars are old, metal-poor, found in the galactic halo and bulge, orbiting in random directions, some even orbiting retrograde, opposite to the galaxy's rotation. These stars formed when the galaxy was young, before generations of stellar death had enriched the interstellar medium with heavy elements. Above and below the galactic plane, population 2 stars dominate. They're time travelers, witnesses to the galaxy's early history, moving on orbits that carry them far from the galactic disk. Some of them might be 13 billion years old, nearly as old as the universe itself. If these stars have planets, and some of them probably do, those planets are bizarre by our standards. They're made almost entirely of hydrogen and helium, with almost no heavy elements. No iron cores, no rocky surfaces, perhaps just tenuous gas worlds or strange objects we haven't imagined. Could life exist on such planets? Could it have existed billions of years ago, when these stars were young, when the universe itself was young? If so, those civilizations would have had a huge head start, evolving for billions of years before Earth even formed. Where are they now? Did they leave traces? Did they spread through the galaxy? Did they vanish, failed, extinct despite their ancient origins? These are questions without answers, mysteries written in the stars above and below the solar system. And there's another population, a hidden one. Population 3 stars. These are the first stars, formed from pristine gas in the early universe, containing absolutely no heavy elements at all. They've never been observed directly because they all died billions of years ago, but we're certain they existed because someone had to create the first heavy elements. Population 3 stars were probably enormous, hundreds of times the mass of the Sun, burning brilliantly and dying quickly in catastrophic supernova explosions that seeded the universe with its first metals. Their remnants might still exist as black holes, scattered through the galactic halo, dark and invisible, but detectable through gravitational lensing. Above and below the solar system, in the distant reaches of the galactic halo, these primordial black holes might lurk, fossils from the universe's first generation of stars, holding within their event horizons information about conditions in the early cosmos.
Now let's consider something truly vast. The Shapley supercluster, the largest concentration of galaxies in our cosmic neighborhood. It contains thousands of galaxies, lies about 650 million light-years away, and exerts a gravitational pull on the local group, tugging on the Milky Way and Andromeda, affecting our motion through the universe. This supercluster is not above or below the solar system in any simple sense, but it represents the kind of structure that exists at the largest scales, the kind of gravitational influence that shapes the motion of galaxies across hundreds of millions of light-years. We are falling toward the Shapley supercluster, slowly, along with all the other galaxies in our region of space. Our motion is not random. It's shaped by the distribution of mass in the universe, by the structures that lie in different directions, by the gravitational landscape of the cosmos. And this gravitational landscape has depth, literally. In some directions, there are vast overdensities, regions where matter has accumulated, creating gravitational attractors. In other directions, there are voids, underdense regions, places we're being repelled from or at least not attracted to. The result is that galaxies flow through space like rivers, following paths determined by the cosmic web, by the filaments and voids that give the universe its largest structure. Above and below the solar system, in three-dimensional space, this flow continues, connecting us to the most distant structures in the observable universe. Let me tell you something that will bend your mind. Ready? Every atom in your body has been somewhere else before. The hydrogen was forged in the Big Bang. The carbon, nitrogen, oxygen, everything heavier was made in stars, expelled into space by stellar winds or supernova explosions, drifted through the interstellar medium, was incorporated into the molecular cloud that would become the solar system, condensed into the sun and planets, and eventually found its way into your body. But it didn't just drift aimlessly. Those atoms traveled. They moved through regions above and below what would eventually become the solar system. They were part of supernova remnants, expanding shells of hot gas enriched with heavy elements. They were part of molecular clouds, cold and dense regions where new stars were forming. They were part of the interstellar medium in all its phases, exposed to cosmic rays, illuminated by starlight, shaped by magnetic fields. Your atoms have memories, in a sense. Encoded in their isotopic ratios, in their relative abundances, in their chemical associations, is information about where they've been, what they've experienced, what stellar furnaces created them, what environments they passed through. And those atoms will continue their journey after you're gone. They'll be recycled, returned to the Earth, eventually perhaps returned to space if the Earth is destroyed when the Sun becomes a red giant. They'll drift through the galaxy again, perhaps be incorporated into new stars, new planets, new life forms billions of years from now. You are temporary. Your atoms are nearly eternal. They were here before you, they'll be here after you, and they connect you to everything else in the universe, to structures above and below the solar system, to stars long dead, to worlds not yet born. This is the ultimate answer to what lies above and below the solar system. Not just objects and structures, not just gas and dust and dark matter and energy, but continuity, connection, a web of causation that links every part of the universe to every other part across space and time, through the movement of matter and energy, through the evolution of structure from simple to complex, from uniform to diverse. We are not separate from what lies above and below us. We are made of it. We emerged from it. We will return to it. The distinction between us and the universe is artificial, a product of our limited perspective, our tendency to see boundaries where there are only gradients and transitions. And perhaps this is the deepest truth, the most profound realization, that understanding what lies above and below the solar system is ultimately understanding ourselves.
Let's venture into territory even more abstract, more unsettling, more profound. Because there's a possibility that hasn't been adequately considered yet, one that transforms everything we think we know about what lies above and below the solar system. What if space-time itself is not fundamental? What if it emerges from something deeper? Recent work in quantum gravity suggests that space-time might be an emergent phenomenon, like temperature or pressure, properties that arise from the collective behavior of more fundamental entities. Just as temperature emerges from the motion of molecules, space-time might emerge from quantum information, from entanglement, from relationships between quantum states that we don't yet fully understand. If this is true, then asking what lies above and below the solar system is like asking what lies north of the North Pole. The question assumes a structure that might not exist at the deepest level. Space and time might be approximations, useful fictions that work well at human scales, but break down at the extremes. At the Planck scale, distances of about 10 to the negative 35 meters, space-time might dissolve into something else entirely. A quantum foam, perhaps, where the very concepts of distance and duration become meaningless. Or a network of quantum connections, nodes of information linked by entanglement, giving rise to the illusion of continuous space when viewed from our macroscopic perspective. What would this mean for the structures we've been discussing? The Oort cloud, the heliosphere, the galactic halo. All of them would be patterns in this deeper substrate, ripples in a quantum information field, emergent structures built from entanglement and quantum correlation. And here's where it gets truly strange. If space-time emerges from quantum entanglement, then the structure of space itself depends on quantum measurements, on observation, on consciousness perhaps. The universe might be participatory, as physicist John Wheeler proposed, requiring observers to actualize reality, to collapse quantum possibilities into definite outcomes. This sounds like mysticism, but it's grounded in real physics, the measurement problem in quantum mechanics. The question of how quantum superpositions become definite classical outcomes remains unsolved. We don't know why observation seems to collapse wave functions, why measurements create reality rather than merely revealing it. And on cosmic scales, this problem becomes even more acute. Who or what measured the early universe, causing it to evolve from quantum possibilities into the definite classical space-time we observe? Did the universe bootstrap itself into existence through some kind of self-measurement? Does consciousness play a necessary role in cosmic evolution? These are not idle philosophical questions. They touch on the nature of what lies above and below the solar system at the deepest level.
If reality is participatory, if observation creates actuality, then the structures surrounding us exist in some sense because we observe them, because we're here to measure them, because consciousness has emerged to collapse quantum possibilities into definite outcomes. Consider the anthropic principle, the observation that the universe seems fine-tuned for life. The fundamental constants of nature, things like the strength of gravity, the mass of the electron, the speed of light, all of them have values that fall within incredibly narrow ranges that permit atoms, stars, planets, and ultimately life. Change any of these constants by a tiny fraction, and the universe becomes sterile, unable to produce complexity. Why? One possibility is the multiverse. Perhaps there are countless universes, each with different physical laws, different constants, and we find ourselves in one of the rare ones that permits life, because only such universes can produce observers. We exist in this universe precisely because this universe allows us to exist. The anthropic principle explains the fine-tuning through selection bias. We necessarily observe a universe compatible with our existence. But this raises disturbing questions. If there are infinite universes with random constants, then there should also be universes where random quantum fluctuations create conscious brains with false memories, so-called Boltzmann brains. In most universes, these spontaneous consciousnesses would vastly outnumber consciousnesses that evolved naturally through billions of years of cosmic history. Statistically, you're more likely to be a Boltzmann brain, a random fluctuation that popped into existence 1 second ago with false memories of a life that never happened, than to be a real person who evolved naturally through billions of years. Your entire experience, your memories of reading this text, your sense of identity might be illusion, a momentary coherence in quantum chaos, destined to dissolve back into randomness in the next instant.
Most physicists reject this scenario as absurd, but it highlights deep problems in cosmology. If we take seriously the idea of infinite universes, infinite time, infinite quantum fluctuations, then we must confront these paradoxes. The structures above and below the solar system might be real, or they might be elaborate hallucinations generated by quantum randomness. Let's shift to something more concrete, but equally profound: the Fermi paradox. If the galaxy is billions of years old, if planets are common, if life arises readily, if intelligence evolves naturally, then where is everybody? Where are the alien civilizations? Why haven't they colonized the galaxy? Why don't we see evidence of their presence above and below the solar system, throughout the cosmic structures we've been exploring? Many explanations have been proposed. Perhaps life is rare. Perhaps intelligence is rare. Perhaps technological civilizations destroy themselves quickly. Perhaps they're hiding. Perhaps they're here, but we don't recognize them. Perhaps interstellar travel is impossible or impractical. But there's another possibility, darker and more troubling: the great filter. The idea that there's some barrier, some challenge, that prevents civilizations from becoming star-faring and long-lived. This filter might be behind us, something incredibly unlikely that we already passed, like the origin of life or the evolution of complex cells. Or it might be ahead of us, some future challenge that destroys civilizations before they spread through the galaxy. If the great filter is ahead, then the silence above and below the solar system, the absence of alien megastructures and starships, is a warning. It means that something awaits us, some disaster that befalls every civilization that reaches our level of development. Nuclear war, climate collapse, artificial intelligence catastrophe, nanotechnology disaster, something we haven't imagined yet. The emptiness of space becomes ominous when viewed through this lens. The structures above and below the solar system, devoid of technological signatures, suggest either we're alone, which seems statistically unlikely, or that something prevents civilizations from surviving and expanding, which is terrifying. Or perhaps civilizations do survive, but transcend physical space. Maybe advanced intelligence inevitably moves into virtual realities, into simulated worlds that offer more freedom and control than physical space. Why explore the galaxy when you can create infinite universes in simulation? Why build Dyson spheres when you can simulate stars more efficiently? This possibility suggests that above and below the solar system, in the galactic halo and beyond, there might be civilizations that have withdrawn from physical reality, living in computational substrates, invisible to our telescopes, because they've deliberately minimized their physical footprint to maximize computational efficiency. We might be surrounded by intelligence operating on principles we don't understand, using technologies we can't detect, pursuing goals that would seem incomprehensible to us. The structures above and below the solar system might be permeated with consciousness, with purpose, with design, and we simply lack the sophistication to recognize it. Or consider this: perhaps the universe is a simulation, a computational process running on hardware in some higher reality. This hypothesis, taken seriously by some physicists and philosophers, suggests that everything above and below the solar system, everything we've discussed, is code, information, mathematical relationships instantiated in a substrate beyond our ability to observe. If we're in a simulation, then the structures surrounding us exist only insofar as they're being computed. Distant galaxies might not be rendered in detail until we observe them, like video game landscapes that only load when the player approaches. The Oort cloud might be a sparse data structure, most objects not fully simulated until they become relevant to the simulation's purposes. This is untestable, unfalsifiable, possibly meaningless. But it highlights how little we truly understand about the nature of reality. The confident descriptions of what lies above and below the solar system might be mapping the output of a cosmic computer program, describing patterns in code, mistaking simulation for fundamental reality. Let's talk about entropy, the arrow of time, the tendency of closed systems to move toward disorder. The second law of thermodynamics is one of the most fundamental principles in physics, governing everything from the direction of time to the ultimate fate of the universe. Above and below the solar system, entropy is always increasing. Structures break down. Stars exhaust their fuel. Galaxies will eventually use up their gas. Black holes will evaporate. In the far future, perhaps 10 to the 100 years from now, the universe will reach maximum entropy, a state of heat death where nothing interesting can happen anymore, where all structures have dissolved, where only isolated particles drift through an expanding void. This is the ultimate fate implied by our current understanding, not a dramatic ending, but a gradual fade into darkness and silence. The structures we've been exploring, the Oort cloud and heliosphere and galactic web, all of them are temporary, destined to dissolve as entropy claims everything. Unless there's a way out, some physicists speculate about quantum tunneling to new universes, about advanced civilizations that might escape heat death by creating new cosmic domains, about cyclical models where the universe periodically renews itself. But these are speculations, hopes, not established science. The arrow of time points toward oblivion, and all the beauty and complexity above and below the solar system will eventually succumb to entropy's relentless increase. Yet, there's something remarkable about our moment in cosmic history. We exist during the brief window when the universe is neither too young and simple, nor too old and disordered. We live in the era of stars and galaxies, of planets and life, of complexity and consciousness. This window might span only 1 trillion years or so out of an infinite future. Why now? Why do we find ourselves in this special epoch? Well, the anthropic principle again.
we necessarily observe a universe at a stage that permits observers. But it's still striking that we exist during what might be the universe's golden age, the brief period when maximum complexity is possible. And perhaps that's meaningful. Perhaps consciousness, intelligence, understanding, these things that allow us to contemplate what lies above and below the solar system are not accidents, but inevitabilities. Perhaps the universe tends towards self-awareness, towards beings that can reflect on their own existence and comprehend the cosmic context they inhabit. This is speculation, bordering on mysticism, but it's grounded in a real observation. The universe has produced structures of ever-increasing complexity. From elementary particles, to atoms, to molecules, to cells, to organisms, to consciousness, to civilization, there has been a progression toward greater organization, greater information processing, greater self-awareness. Does this trend continue? Will future intelligence transcend biology, merge with technology, spread through the galaxy, reshape reality itself? Or will we remain confined to Earth, one species among billions that arose, flourished briefly, and vanished, leaving no mark on the cosmos beyond a few radio signals that will fade to invisibility as they spread through space? These questions have no answers yet. The future is unwritten, but they frame what lies above and below the solar system not just as existing structures, but as potential resources, stages, canvases for future intelligence to explore and utilize. The Oort cloud might become a reservoir of raw materials for massive engineering projects. The heliosphere might be deliberately reshaped to optimize conditions for interplanetary civilization. The galactic halo might host outposts of far future civilizations, being so advanced that we would seem to them as bacteria seem to us. Or it might all remain pristine, untouched, beautiful in its natural state, a cosmic wilderness that intelligence chooses to preserve rather than exploit. We stand at a threshold, looking outward and upward, contemplating immensities that dwarf human comprehension. What lies above and below the solar system is possibility, mystery, challenge, wonder.
It's the Oort cloud, with its trillions of icy sentinels, marking the boundary of our sun's domain. It's the heliosphere, our protective bubble in the interstellar sea. It's the scattered disk, with its bizarre orbits, hinting at hidden planets. It's the galactic halo, with its ancient stars and dark matter. It's the cosmic web, connecting all galaxies in a pattern of filaments and voids. It's dark energy, pushing space apart. Its quantum fields vibrating with zero-point energy. Its gravitational waves rippling through space-time. Its neutrinos carrying information from stellar furnaces. Its magnetic fields channeling cosmic rays. It's the interstellar medium in all its phases, birthplace of stars. But more than any specific structure, what lies above and below the solar system is the future of understanding itself. Every answer we find generates new questions. Every mystery we solve reveals deeper mysteries. The more we learn, the more we realize how much we don't know. And perhaps that's as it should be. Perhaps the universe is inexhaustible, infinitely deep, always offering more to discover, always presenting new puzzles, always surprising us with phenomena we never anticipated. We've gone from thinking the solar system ended at Neptune to recognizing it extends thousands of times farther. We've gone from imagining empty space to discovering it's filled with invisible matter and energy. We've gone from believing time flows uniformly to understanding it's relative and flexible. We've gone from seeing the galaxy as static to recognizing it's dynamic and evolving. What will we discover next? What structures above and below the solar system await detection? What phenomena beyond our current imagination exist in the depths of space? The journey has only begun. We've taken our first halting steps into the cosmos, sent a handful of probes to the outer solar system, observed the universe with increasingly sophisticated telescopes. But we're still essentially confined to our home planet, still learning the most basic facts about our cosmic environment. Future generations, if we survive and thrive, will know so much more. They'll have mapped the Oort cloud, identified Planet 9 if it exists, sent probes throughout the heliosphere, established colonies in the outer solar system, possibly even ventured to other stars. They'll look back at our era with the same mixture of affection and amusement that we feel when we read about early explorers who thought the Earth was flat or the sun revolved around Earth. And they'll still be discovering what lies above and below the solar system, because the universe will still be revealing its secrets, still unfolding its mysteries, still offering infinite depths to explore. This is the conclusion, the realization that there is no conclusion. What lies above and below the solar system is not a final answer, but an eternal question. It's the universe itself, vast and ancient and mysterious, filled with structures we've discovered and structures we haven't, phenomena we understand and phenomena that remain beyond our comprehension. We are part of this universe, made of its matter, shaped by its forces, evolved through its processes. And we are the part of the universe that wonders, that questions, that seeks to understand. We are stardust contemplating stars, atoms organized into consciousness, the universe awakening to its own existence. What lies above and below the solar system is everything. The past that shaped us, the present that contains us, the future that awaits us, the mystery that calls us, the beauty that inspires us, the infinity that humbles us. And it's ours to explore, to understand, to marvel at, for as long as we exist and wonder, and reach toward the stars. The cosmic structures surrounding us are not just objects to study, but invitations to adventure, challenges to intelligence, reminders of how much more there is beyond our small world, beyond our brief lives, beyond anything we've yet imagined. Above and below the solar system lies the cosmos, and the cosmos, in all its terrible beauty and magnificent complexity, is home.